Hi everybody, welcome back. We're going to try the camera at a little bit different angle this time, just for fun. And what you see in the background here next to me is a Rotel model RA-1412 integrated amplifier, which is going to be our project for this video. It kind of went in directions I never expected it to go. This amp was in very good condition when it came onto the bench. It really didn't have a lot of problems. But after testing it a little bit, it did have a small issue. It turned out to be a minor problem, but because of a mistake that I made along the way in setting things up, it led me on a wild goose chase that ended up, once I figured it out, once again, there wasn't really a whole lot wrong with this thing. So we got it all fixed. It's working perfectly. But I think I'm going to do the video based on that. That's going to be the key point of this, not how to restore or to service one of these Rotel amplifiers, because it's really very straightforward. The design of this amplifier is very similar to many of the ones I've done previous videos on. So what I thought I would focus on right now is how making this one mistake that I made how it will change the symptoms of what the amplifier performs like and can make you think that there's something wrong when there really isn't. Especially when you're chasing, an actual problem, which was, like I said, it was a more minor problem, but it made it look like it was way worse than it really was. So I won't spoil the rest of it, but that's it. Really what I was going to do originally was do some minor cleanup and alignment on this, and I really wanted to focus on some of the testing methods. I wanted to try a new application that I installed on the MDO2204 up there, and actually was going to focus on that, but we're going to save that for the next video. I'm going to do that right now. I'm actually setting up to do those tests, and that'll be another video. But this video is going to be the troubleshooting of the amplifier and of Tony and how it all turned out. But the good news is this amp is solid. It's in great condition. It's working perfectly, and we'll check after we do our tests in the next video to see if there's anything else we can do to it to make it better, or if there are limitations in the design of this. But I'll let you know, this is a really well designed amp. I really like it. So anyway, that's enough. Enjoy the video, and we'll see you at the end. Hi everybody, welcome back. Well, here's our next project. It is a Rotel model RA-1412. And I got this thing. It's kind of a neat project for me, because back in the early to mid 80s, when I worked at an audio shop, they got a lower end model of this. This one's rated, I think, at 150 watts per channel, if I'm not mistaken. And the one that I purchased was 90 watts per channel. I'll have to look up the model number. I forget what it was. But other than that, the front faceplate looked almost identical to this one. This one has dual power supplies in it for right and left channel, and the one I had a single power supply, so it was just a little bit lower end model. But I really liked it. It was a great piece of audio equipment. It was built like a tank. This thing weighs a ton, and so did the one I had. And I owned that clear up into the 1990s. But I never really used it a whole lot because of, where I was in my career and everything. So it kind of sat in storage, and one of my colleagues at work expressed an interest in purchasing another integrated amplifier for his system. And being, young and just getting into, my career and everything, I really needed the money, so I sold it to him. So probably to this day he still has it. I don't know. He used it to, I guess, I forget what kind of speakers he had or whatever. But anyway, ever since then, I've always, I remembered that amplifier very fondly. So my friend was able to find this one at a really good price and procure it. So we're going to go through and restore it if it needs it. I don't even know what all it needs or doesn't need. And then we're going to test it out and see how it performs. So if that sounds interesting to you, that's what we'll be doing. Stay tuned. Now, in my experience, from the smaller model that I had, these things were a complete work of art. You can tell that a lot of care and a lot of planning went into the design and build of these amplifiers. Now, I haven't worked with a lot of Rotel gear. I've worked on some turntables, and of course the unit that I had, which I really didn't do much to. The little story behind that, you know, you got to have the Tony story, right? When I worked at that little audio store, that Rotel amp came in as a trade-in, so it was a used unit, and it went on the shelf. And when I came into work the one day, I saw it sitting there, and I said, "What's this?" You know, and the owner of the store said, "Well, it came in on consignment. You know, we traded it in. He bought a big ADCOM system, component system, and traded this in." And I said, "You know, how much is it selling for?" And he says, "I'll sell it to you at cost, what I paid, you know, what I have in it." And I forget what it was, but it was either $200 or less than that. It was very inexpensive. And I thought even back then in the mid 1980s, that was a great price for something with this kind of build quality. And I asked him, "Does it work?" And he says, "Yeah, it works perfectly." You know, I hooked it up real quick and listened to it. Of course, so I took it back on the bench and hooked it up. It worked just perfectly. It didn't need anything. And it was in mint condition, so I bought it. So that's how I got it. Anyway, let's take the cover off. And again, this one is definitely a level higher than the one I had, with the dual power supplies, cap banks. There's your two amplifier modules. Here's your input section over here. And look at your line, stage, and tone control section. Look at that board. Just look at the printing on that and everything. Absolutely fabulous. I love the way these things are made. Great big 8-gang volume and balance control pot. So yes, they do make 8-gang stepped attenuators still, so you can get them, but they don't look like this, and they are exorbitantly expensive. So this is one thing we never ever want to see go bad. As far as capacitors and things are concerned, there's not a whole lot of them. I mean, you look on these amp modules, most of them are like that though, really. You have 1, 2, 3, 4 electrolytics. And that's all I can see right offhand. I don't know if you're seeing, I'm kind of hand holding the camera here. And to look at anything else, you're really going to have to take the bottom off and look at it from underneath. Flipping this over and look at the underbelly, we can see that there's some corrosion. It probably tells me it was sitting in a basement or something. And I don't know, let's see if we can, I cannot, with the naked eye, I cannot see this, but there is a date on there. And February 17th, we can make that out pretty easily. And let me turn some lighting off. I don't know if we can, I just want to see if we can see what there's a 19, but the last 2 digits are missing. And I don't know. Let's take this off. Wow. Very, very clean. And you can see your 2 separate power supply boards. So one there and one there. Here's our input board. I'll be honest, there's probably not going to be much of anything that we're going to have to do other than clean the controls a little bit. All of these are attenuators. They're not pots, as per se. I don't think there's any pots in this whole thing. They're all switched attenuators. And you can see the knobs are machined aluminum with big set screws in them. I mean, this thing's more built like a commercial, you know, radio type thing. So, and just little attentions to detail, like how they soldered the ground terminal on so it doesn't come loose. I don't know if you could see that down in there. Just things like that. Built like a tank. Let's get some schematics. Okay, we have a little bit of shutter roll on this from the lights. I have them, hopefully it won't be too bad, but we're just going to deal with it. So let's do a quick look at the schematics. There's not a whole lot to really talk about. A few things that I think are very interesting. This is a very well laid out amplifier. It is extremely well designed, I think. Very basic, very textbook common design. So there's nothing special, but it's just the way they executed it. They did a really good job. And you can see there's your right and left channel independent power supplies. And each side has a 22,000 microfarad capacitor for the positive and negative rail. So that's, for instance, this is a 110 watt per channel amplifier. We did a couple of Pioneer SX1050s that are rated at 120 watts per channel, and they have a single toroidal transformer, but they only have a 22,000 microfarad, I think, for both channels combined. So a lot of reserve here in the cap bank. And of course you have just a simple passive regulator here that they use for the low voltage supplies. You can see them right there. The protection circuit is, again, pretty basic. It gives you a delayed turn on so that you don't hear the capacitors charging and get the big pop sounding in the speakers, and it drops out the relay to the speakers whenever you turn the unit off, so you don't hear a pop again. They did a really good thing here. You can see that the normally open contacts, or the normally open contacts are tied to ground, so that when the relay releases, it grounds the contacts and it grounds the speakers. And that's pretty important because a lot of the designs out there don't do that. And one of the things that this will do is, by taking your speakers to ground when it shuts off like that and goes into protect mode, any of the reactive components inside your speakers, whether it be the components of the crossovers or the inductance of the actual speaker voice coils themselves, all of that has to release its energy, which can still be damaging to your speakers, and also can cause a lot of arcing on your contacts. So by having these contacts grounded like this, that really reduces that, and that should mean that this relay is probably going to last a very long time, and the contacts are probably going to be in very good condition when we check them out. Here's your amplifier, for one channel. Very simple. It does have one little unique thing from a lot of the designs we've looked at. You, of course, have your differential input, and you have your DC bouncer, your offset adjustment, as we call it. You have your bias spreading circuit, and this is the bias pot to adjust your bias level. But you have this third potentiometer on here, and it actually adjusts the sensitivity of your protect circuit. So by adjusting this, you're adjusting the threshold to where this can trip your overload protection. So that's kind of unique. And what they have you do is they have you feed a 100 hertz signal at a certain level in here, and then adjust that pot till the signal trips, I believe is how they do it. We'll have to read through it again to be sure. But that's a neat little feature. Other than that, all of this is very straightforward. You've seen it before. Going to the other page, you have your multi-gang potentiometers. So if you notice, you have a volume pot here and a volume pot here at the input of the line stage, and then you have another volume pot here and volume pot here at the output of the line stage. So you're attenuating the input and the output. You have the two pots for the balance, and that's all in that great big stack that we were looking at over here. You know, 1, 2, 3, 4, 5, 6, 7, 8. Although, just a quick look at the schematic, I see 1, 2, 3, 4, 5, 6 elements. I haven't seen the other 2 elements yet, but of course I haven't been looking very carefully. But pretty interesting how those are all ganged together. Hopefully we will never have to replace this. And you can see all of the tone controls are not potentiometers. They are stepped attenuators. So the only pots in here other than the calibration pots is the mic mixing level and the volume and balance pots, which are pretty sealed, and I think they'll be okay. We'll look at them. We'll test them out. So really there'll be some contact cleaning that we'll do, a little bit of maintenance on that, but it shouldn't be too bad. Again, very straightforward schematic. There's nothing special in here, and it's just the execution of it is, in my opinion, is very good. They did a good job laying the circuit out. Good choice of components. So we'll see. And really, for being such a big amplifier, not a whole lot of electrolytic capacitors. It's just a good bulletproof design. So what I'm going to do is we're going to connect this up and we're going to test it out, and we're going to see how it performs before we do anything to it at all, because I have a feeling this amp's going to work just fine. My, how things can change between 2 video clips. Let me give you an update. I connected this up to the power supply, or I mean to the isolation transformer, you know, put it on the dim bulb, made sure it came up. Everything came up really well. Everything measured perfectly, looked good. I applied some signal to it. It passed the signal. Everything was good. I took it off the leash. It worked really, really well. I played some music in it, and it just absolutely blew me away how wonderful this thing sounds. This thing has an amazing sound to it. A really nice warm sound, lots of powerful bottom end bass, really crisp highs, very open mid-range. It's the whole combination, and this is without doing anything to it. So I was listening to it, and I was about 4 songs into my listening. I kind of got wrapped up in it because it sounded so good. And I was listening to it at, maybe about no more than between 1 and 3 watts per channel. Of course, these clip speakers are pretty efficient, so if you get much louder than that, it starts shaking the floor upstairs, and people don't like it. And I'm in the middle of listening to a song, and all of a sudden I heard this loud kind of a shrieking, crackly sound, and bang, the protect circuit came in right away and locked out, and that was that. So I turned it off right away and turned the camera on. That is where we are right now. So I don't know if something just shorted out, and I don't know if I turn this on if it's going to come out of protect or if we're going to damage something further. So what I've done was I turned it back onto the dim bulb, and these capacitors are fairly hefty. So for this thing to come up, being dual power supply, I have 2 bulbs in. I have a 100-watt bulb and a 40-watt. So I have about 140 watts of current limit right now in the bulbs. And we're going to turn this back on, and we're going to see if it, A, if there's a short, and B, if it will come out of protect. Now, depending on how it acts, there could be any number of problems, but I don't want to overguess it. I would rather just observe and see what happens. So let me do this. We're going to put the camera kind of at an angle like this, And if you, let's turn this light off, get a little bit less glare and so forth on it. And you can see the light right here. This is the protect light. If it comes in, that means that it's not going to let the relay, the speaker relay, come in. I've disconnected the speakers and I've connected to the 8 ohm dummy load. And I have these two bulbs enabled. So now let's turn the power on. Let's see what the bulbs do first of all. And you saw how bright those got. That's because of those massive capacitors. But you can see they went totally dim, barely a glow to them, and the protect dropped out. So the amp is turned on right now. All right, let's do some speculation. What could cause this? We know that it failed after about 10 minutes to 15 minutes of listening. I was at a low volume level, so I wasn't really pushing the amp very hard. I didn't measure all of the voltages at all the points. Of course, you can't do that in the amplifier. But this, to me, looks like a very telltale sign of a small signal transistor that's leaky. And when it warms up, the transistor shorts, or it leaks to the point where it puts excessive DC onto the amplifier circuit and causes the circuit to trip, the protect circuit to trip. Now, the idea of this is we need to, believe it or not, I can see that those bulbs are glowing more as we are standing here talking, okay? They had almost gone completely dim. And now if you look, they are actually starting to get a little bit brighter. Now the camera, I'm sure, is going to compensate, for the lighting and so forth, but I'm actually watching these bulbs get a little tiny bit brighter as time goes by. So you're getting DC somewhere where you shouldn't. Now what I want to do is just kind of hang out here for a little bit and see if something goes and runs away and we get kind of crazy voltage. Let's also, while we're at it, I'm going to do this. I'm going to focus you in a little bit, zoom you in, I should say, a little bit more. And you can observe, I don't know if you can see with the glare or the lighting or anything. Let me turn off some lights. Here we go. That really doesn't help, huh? So let's do something with the, I don't know if I can, I'm playing with the white balance on this, and of course nothing happens. So I'm not going to fiddle with the camera a whole lot, but let's keep looking at it. It looks like we're getting 468 milliamps, and of course because of the bulbs we're only allowing about 104 volts out to the amplifier circuit. I think what I'm going to do is I'm going to shut this one off and turn this bigger one on, which is going to allow a bit more current to flow. Now we have 110 volts and 562 milliamps. And I just want to see if the current goes up. And yep, 565, 566. And now it's hovering around 567. Now it's down to 63, 68, 72. So I don't know if you can see that or not. Let's see if we can get a little better angle here on this camera. This camera is really stiff, this thing. Hope I don't make you too up. There we go. We just went into protect, and it's still drawing that current. I don't know if you can see that now. Hopefully you can see it a little bit. We just went into protect mode. All right, so we know we can get it to repeat itself. I'm going to shut off, and I'm going to get the amp on its side, and we're going to try to isolate between left channel and right channel now. Because we know now if we hold this on long enough, we can get it to fail. So we can measure it. I spy with my little eye our first problem, but I do not think it's what's causing the issue. Do you see it yet? Maybe not. Let me zoom in. You see it? So let me unplug the power. And let's move this out. Yep, something failed. I would say that is a faulty capacitor. Now, that is a across the line capacitor, and this was just a film type capacitor. Wasn't an actual safety capacitor. So it probably just failed, and I don't believe in any way that that could cause the protect circuit to trip, because the protect circuit is only affected by the DC voltages that are present in the amplifier power, the other side of the power supply. So I'm going to just clip this out for now. We can always put a new safety capacitor in there afterwards, but I don't know if you could see, it's just falling apart. So let me bring that back so you could see as I shake the camera. But yeah, that thing's pretty shot. So we'll get that out of there. I'm now going to continue on, and we're going to just look at these. Here's your two power supplies. Let me connect up. Okay, I measured these supplies, all of them, both in non-failure mode and in failure mode, and none of them really dropped significantly, if at all. That's good news, because what it means is you don't have anything drawing really heavy current. So it's just as I suspected. We have a small signal transistor that is leaky, and it's causing the bias to go off, which tells me our problem is going to be here, because what's happening is something in here is drifting on one side or the other, and it's causing an imbalance between these. And by the way, this is a quasi-complementary output section, so it's similar to the video I did on the Sansui 9090. The original 9090s had a quasi-complementary output where all four outputs are NPN, whereas a true complementary would have NPN on one side and PNP on the other. So this is a little bit older design, but they work really well. So anyway, this isn't drawing heavy current because it's dropping out of this, dropping the load off when the relay pops. And all this means is that there's an imbalance between the two, the push and pull side, between the two rails, and that's being caused by something here that's throwing off your bias. So it could be one of these transistors is bad in the differential pair. It could be one of the bias transistors. Any place around here could be fair game. My guess is going to be either one of these guys or one of these guys here. We'll see. I don't think these drivers are going to be the culprit, although they could be. I don't think they will be, though. I think we're back in this section here. So let's see if I'm right. Okay, I just moved these meters on the bias. So this is the bias for the left channel. This is the bias for the right channel. You can see this is staying really nice at about 30 millivolts. This is going bananas. You can see it. So we're getting pretty bad bias creep. Let's see if you can see that meter a little better. If I move there we go. How's that? It's way over now. And if I show you up here on the scope, if I just barely turn this up a little bit, it works. Everything looks good, but with that tiny little signal, look at the bias on the one channel, look what happens to the bias on this channel. So you have a transistor that is severely failing. And I believe it's one of those two bias transistors. So we're going to have to definitely deal with that. Although I may use the oscilloscope to see if we can probe around and kind of look at a couple of these signals in different parts of the circuit so that you can actually monitor this and see what it looks like. Okay, we're looking at both channels now at the junction of these two 330 ohm resistors, and these are all carbon composition resistors in all of these areas, and I think they did that instead of the metal resistors, maybe because of the age of this and maybe because of the I don't know, because sometimes people like the carbon comp, I don't know, but I'll have to measure those. But we're looking at this junction point right here, which should look like, if we put a sine wave in there, we should see a sine wave here, which will differentiate these two outputs here and here, or these two drivers that go to your output section. And they should, both channels should be the same, all things being equal. So here we go. And you can see they are. So really the only thing that's happening is we're drawing excessive current on the other side because of the bias creep. And you can see this channel just keeps being wacky. So let's see if we can turn this down a little bit and if it'll stay. Okay. That was, let's take this. These pots are really crunchy. We're going to have to clean them. That's about as good as I can get that one right now. Let's see what happens now. And they're still driving the same. See right there. And you can see it's creeping up again. This one's holding rock solid on the right channel, left channel. The more we drive it, it just kind of creeps around. Okay, here's another problem. If you recall, this thing is loaded with those carbon comp resistors, those carbon composition. And carbon comps can definitely drift with age. So for instance, these two that are in line here, those are 330 ohm resistors. And just because it's a pain to get on them, I'll show you one, and I'll tell you what the other one was when I measured it. Let me see here. Right here and here. I think this is it. Yeah. So our 330 ohm is now 372, and this other 330 ohm is 353. So yeah, they've drifted up, and that's pretty much what these do. So they're going to need replaced. And the other problem with these with carbon comp resistors is, as they heat up, they change in resistance. They drift. So we're going to put some metal film or metal oxide resistors in there, and that will not drift, and that'll take care of it. It's a lot of work now, because now we're going from just replacing a few capacitors and one transistor to now I have to go through these boards and check every single resistor, and it's kind of tough around all these wires because you're still tethered to these transistor wires from the transistors. So it's kind of a pain to get around there. But there's no other way to do this. I mean, we have to replace the components that are bad. So like I said, we're in there. I'm not going to mess around. We're going to replace it. Now these other smaller ones quite often don't drift. These might be carbon film instead of carbon composition, but I don't know yet. I'll have to measure them to see, and they may be a little more stable, and if they are, we'll be good. The only ones we'll have to worry about is these in this section in here, and these few over here. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on here. So that's quite a few. It's not about the cost, it's really about just the pain in the butt to replace them, but I think we're going to have to. Alright, we are all back together now, and I did replace the capacitors, and I very meticulously cleaned the 3 potentiometers and set them to exactly the same resistance they were when we started. So hopefully everything will kind of be okay. One thing I noticed on these is if you look over here on this stabistor here that they're using, they have these fiber washers. They have one below it and one above it. So there is actually no thermal coupling taking place at all between the thermistor and the heatsink. Now, I don't know if that's by design or what, but both channels have that. And I don't know why they did that. Of course, there's a little bit of heat from convection. There's a gap in between here and here, but that must be the way it was intended, so I'm not going to change it. I put it back how it was. So I have these 2 meters connected, and what I have is I have this meter connected to look at the DC offset, and I have this meter set to look at the bias. So we have bias and offset. And I'm going to turn this on, and hopefully we won't have any smoke. I do have the dim bulb on, but we'll see what happens here. Alright. And there's our DC offset. And it's dropping down. So we're sitting at 15 millivolts right now of offset, which is not bad, and it's dropping. So you can see as the temperature stabilizes on the outputs, it's getting very low. So I'm not going to touch that. And again, I just kind of roughed in the potentiometer there, so we'll see where it's at. This is supposed to be 30 millivolts, and we're at 26. That's good. So from what I can see right now, it looks as if this channel's working since we serviced it. Now I haven't done anything to the other channel yet. And look at where our offset is now. It's like beautiful. That's perfect. And this is creeping up a little bit. So what I'm going to do is I want to see if we still have that bias creep in here. I think after cleaning the pot and readjusting it, that may have taken care of it. And of course replacing those bad resistors, that's another thing I forgot to mention. It's been a couple days since I've worked on this, so I'm trying to remember where I left off. These 2 330 ohm resistors were, you saw them in the last clip, they were pretty far out. The rest of these carbon comps were all well within the 10% tolerance that they're rated at, so I didn't touch them, I left them in. So, but I did replace these 2 here, and again, those are the only bad ones on the whole board. So let's get some signal on this and take a look and see if it works. But I want to let this idle for about 10 minutes to see if that bias creeps up again, and if we get some weird, high current draw and trip our protect circuit again. As soon as I know that that's going to be okay, we're going to actually look at some signal. So we'll be right back. Okay, this has been on for about 10 or 15 minutes now, and these 2 meters are still connected to the bias and offset for the left channel, and I'm using this one to look at the bias on the right channel. And you can see they have crept up just a little bit, and that's after being on and warming up for 10 or, like I said, 10 or 15 minutes. And they do drift up when you play the amplifier, and it does take a little bit to creep back down as the amplifier cools. So the thermal tracking isn't perfect on it, but it does bring it back down. So it is working. I don't know how effective the bias tracking is on this, because none of the bias stabilizers or anything are actually properly coupled to the heat sinks of the outputs. So it's kind of hard to have thermal tracking the way it's set up. But you can see they're both tracking pretty good. Now here's the problem. I have a 1 kilohertz signal at 250 millivolts going into the auxiliary input, and if I put you down here on the meters, there is a little bit of a concern here. Okay, so I have the muting on minus 10 dB, and I did that simply because I have better control of the detented volume knob. And you can see as I bring the volume up, you can see they are not even. And it's not the metering circuit, because if we look up on the oscilloscope, you can very clearly see that one waveform or one channel is definitely higher in amplitude than the other. And the other thing I notice is this one kind of jumps a little bit when you turn it up and down. Every now and then it does. So I still think we have something going on there with a transistor. I'm not sure. And you can see that happens to be the right channel. And you can see I'm turning the balance control, and it really is not working very well at all. Now that channel, you can see the balance control is working. And you can see when I turn it this way, it does not turn the volume all the way down when I turn the balance. I'll show you what I'm doing here. So this is the knob. Here's the balance control, and I'm rotating this one way. When I turn it this way, it turns the left channel all the way off. If I rotate it all the way this way, and you can see it's all the way there to the left, the right channel does not go all the way off. So I think we have a problem in this potentiometer gang. And of course, famous last words, because I just got done telling you guys a couple days ago when I looking at this that I think this is going to be fine, these don't fail. But here you go. So we're going to have to take this off and clean it. I think that's part of our problem right now. And there, just moving that, it tripped the protect circuit. So there's weirdness going on, and I think it has to do, I think it's a mechanical problem. I think it's this pot. I don't think it's anything electronic on the amplifier. If there was something wrong and you had DC offset causing the problem, you would see that offset right here on this meter right here. And if I take this meter, you can see our bias is behaving pretty well. And if I move this over here as the camera shakes and makes you dizzy, here's pin 5. You can see very, very low DC offset. There is a little bit there though, you can see. Not terrible. That 28 millivolts should not make that big of a difference really. So again, I don't know. I think it has to do with that, with the potentiometers. But I'm going to take them out and clean them. Obviously, there's something strange going on, and we're going to have to address it. Okay, I know I have the camera at a really high angle, but I've reset the amplifier. And again, we have everything set as far as offset and bias. And I have just the volume set, and you can see once again it is very imbalanced right to left channel. But here's the strange thing. If I take the balance control and I turn it to the right, I mean, it works like a balance control, right? Watch what happens as I rotate this to the left channel. So far it's working like a balance control, right? Now here I am right here. I'm not all the way to the left. And you can see I can just about flatten it out right there. But look where the balance control is. It's only here. Watch what happens if I keep rotating it to the left. Yeah, it kind of goes through a null point. Look at that. Very strange. So I don't have an explanation for that. See? I have to watch because the balance control grabs the volume control and drags it with it. Look at that. Odd. I've never seen anything like that before. And there it is back to center again. And you see how everything's jumping around? And then if you mess around too much, it'll trip the protect. So we definitely have something weird going on here, I would say. But tapping it doesn't seem to make that big of a difference. I don't know. Unless there's something going on with, I mean, I don't see anything with DC offset. So there's nothing changing on the amplifier end of things. You can see right here. I mean, that bias is high because there's signal right now, so you can't pay attention to that. But the DC offset, even though you have AC coming out of the speaker terminals, there is no DC offset. So again, I think the next thing to do is let's take the oscilloscope and let's look at what is going to the input of this signal. So I'm going to take this. Okay, I solved the problem. And it has nothing to do with the amplifier. It has everything to do with the person working with the amplifier. I want to show you a really good example of how you can make a simple mistake and lead yourself down a rabbit hole. This is a good learning experience for all of us, so I'm going to share it with you. I went to disconnect those two leads coming from my dummy load so that we can connect up our probes, and we were going to probe the input to the two amplifier modules, right? I noticed when I disconnected the two leads, which are these, it tripped the protect circuit right away. Now why is that? Okay. Well, first of all, let's go through the process. As I said before, when you look, if you watch my oscilloscope series, okay, I did a couple videos on oscilloscopes quite a while ago. But if you look at these inputs, there's two things about the input of an oscilloscope you must remember. And that is, number one, the outer ring, or the common lead of your oscilloscope probe, okay? So for instance, this wire right here on the probe, okay, I know it's not focused, is connected to this outer ring here on the BNC connector, right? It's connected to the shield of the BNC connector. The BNC connector is also connected to ground, to actual ground, which is also connected to the ground prong of your AC mains power cord. Now, in addition to that, these two grounds right here and here for channel 1 and channel 2 are common to one another. That means that these two outer shields on the BNC connector are electrically connected together. It's one connection. They're shorted together, okay? That means when I connect this and this, channel A and channel B, left and right, I am connecting the ground leads of the two speaker terminals for right and left together. Now, that's not a problem, and I'll show you why it's not a problem. Let's back up the camera. You'll understand why I'm saying all this and going through all this in a minute. If you look right here, here is your positive lead of your speaker terminal. So this goes to the red speaker terminal. Okay? And you can see it goes through your, here's your outputs for your push-pull. Remember, this is quasi-complementary. There's your emitters. They go through the emitter resistors on both sides and into here. And then they reference to E3, which is your ground. So your speaker is connected to chassis ground on the ground side. And both channels are tied together. So that should not be a problem, right? Okay, so here's the speaker dummy load board. And so all we're doing is by connecting these outputs up here, both to the oscilloscope, you're tying these two ground leads together. That's okay. That's not a problem. Because, again, according to our schematic, they are both electrically connected that way. And I'll get the big schematic out here and I'll show it to you as soon as I find it. Here it is. So, looking at the big schematic, you can see, again, both the right and left channel reference to ground. So, why, when I connected the oscilloscope to the dummy load, did it trip the protect circuit? Well, I'll show you. What is wrong with this picture? Can you see anything? Those are your speaker leads. The top one is your left channel, the bottom one is your right channel. I reversed the plus and minus when I connected it up. I didn't look around there all the way when I hooked the wire up, and I didn't pay attention. So what does that do? Well, that red lead is now connected to ground, and this black lead is connected to ground. So what was happening was the red lead, this was actually being connected to the ground, and this was connected to the plus. So whenever I connected these two things together, I was shorting this black lead here to this red lead here, which was shorting the one channel. And that's why you were getting that strange looking output like that. It was bleeding across the dummy load resistor and into the scope. So a lot of my problems as far as the weird looking signal was 100% caused by me not catching that. That was the problem. Now we still were getting bias creep because the bias has nothing to do with your speaker leads like that. So we were still getting the bias creep problem, but the weird waveforms being imbalanced and the tripping of the circuit when you turn the volume up was coming from that. Now remember, originally when we started this, it was tripping the protect just sitting idle, and that had very little to do with this problem. That was, we had a genuine problem, and we fixed that by cleaning this pot. But we introduced an additional problem when we hooked it back up and put the speaker leads on backwards. So this last 10 minutes here, I chased my tail because when I hooked everything back up, I swapped those two leads accidentally. Let's switch them back around where they belong now. and let's see if everything works as it's supposed to. And I'm going to do this on camera. I think it's worth the extra time of video so that we can see it. Okay. This is the kind of stuff a lot of people like to edit out to save face, but I really don't care. You call me whatever you want. This is interesting, and if this helps one of you to realize, you know, what the symptoms are when you do things like that, and how easily your test equipment, when things are hooked up wrong, your test equipment becomes a source of a short, then it's worth me having this on the video for you. Okay, we're now connected back up the right way. I'm going to turn the power on. We're going to wait for the protect circuit to drop out, or the relay to come in, whatever you want to call it. And there we go. And we now have volume. Now, I still, unfortunately, have an imbalance of the volume. You could see that. So let's go back to our original thing, and let's look at the inputs now that we have everything wired properly. Okay, as you can see, I have the oscilloscope connected the two channels to the input. This is coming from the volume and, you know, tone control amplifier and everything, and I have that on both channels, and I have the volume up, and of course we're still in protect mode. I'm leaving it that way for right now. And if you look, the amplitude of those two signals is identical. They match right up. So that tells me that the problem is not the volume control. And if I go to the balance now, I turn it all the way left here, I turn it all the way right here, you can see that the balance is working properly. And okay, we're now connected back up. And you can see as I bring the volume up, I'm at 1 watt per channel. According to the meters, of course, 5 watts per channel, and about 9 or 10 watts per channel. And now we're going off the scale, we're at about 15 watts per channel. And as you can see, yeah, there's both channels. They're just literally falling on top of one another almost perfectly. So they're balanced. Now, the one thing I did notice is the metering circuit, now that we know everything's set properly, is slightly off, but not by a whole lot. So if you look there, this one reads ever so slightly lower than this one, and that might be a little tweak of the metering circuit. Okay, after all of that, I have the amplifier warmed up really well now, because if you saw, we were running it at 10 to 15 watts per channel for a while. And after running it back down, you can see our bias has dropped right back almost to 30 millivolts where it belongs on both channels. I don't know if you could see that. And there's your DC offset for the left channel, and I'm sure the right channel is just as good. So everything's working. Okay, I've been playing this for a while and everything's perfect, and yeah, it's working just fine. They're balanced, everything's good. So I'm going to go ahead and recap this side over here so that it matches this side. Again, I think everything's working. I don't see any reason to go any further than that. And once I do that, we'll give this one last test. And this amp should be in pretty good condition. I'm just going to clean up these controls down here a little bit, which don't really need it. They're pretty clean. And this amp will be ready to assemble and actually do some testing on. And we'll do some final alignments of the metering circuit to make sure that it's balanced. And I think we're good as long as we don't put wires on backwards again. By the way, this thing is a lot easier to take apart than it really looks. The sides come off of this, the side panels, independently. So it makes it very easy. There's an inner chassis, and then the side panels wrap around the outside, so it makes it really accessible. So you can see the input board, how easy it is to get to. And to take the amplifier modules out, you take this side panel off. On that side, you don't even need to take the side panel off. All you do is you disconnect the stabilizer by loosening this screw and sliding that out. I took this aluminum plate out by taking these two screws out, and then you just take this screw and this screw down here right out, and then the board just kind of tips forward and pops out. The only thing you have to watch is, if you look very carefully, hopefully I can get it in the camera. Do you see right down there? If it will focus for us. Yeah, there it goes. This little plastic piece right here, that's a spacer. That has to be in there, and it's on both sides. There's a spacer here and a spacer there. But down in the bottom, there's just a little spool type plastic piece, and this just clips down onto it. So it's very easy to disassemble. Now, on the over here on the left channel amplifier, I chose to take these top pins out. I just desoldered them. It made the board a little bit, it allowed me to swing it forward a little bit more. This one came out enough that I didn't even have to do that on this one, so it came out really fast. To replace the 4 capacitors in here and the 2 resistors, which they were, one of them was in tolerance and one of them was almost on the edge of being out of tolerance, so I replaced them as well. But just like the other channel, all of the resistors tested good other than those 2, and all of the 4 capacitors tested perfect, so they really didn't need replaced. But like I said, while I had it apart, I changed them. So taking it apart is as easy as those 2 screws. Now the side panel, I'll show you how it goes together. It's equally as easy. There's a bunch of screws, but really it's not hard at all. This inner panel goes on like this, and then you just put all the screws in, and then once that's in, this part right here, you see there's 4 screws here, 1, 2, 3, 4. You take those out, and then once you get all these other screws out around here, you can just kind of wiggle this a little bit and it slides out and pops right off. Real easy. Believe it or not, I had this apart and had the amplifier module tipped down and ready to replace the components within 10 minutes. Took another 10 or 15 minutes to replace the couple of components that we replaced, and everything's good to go. So I'm just now going through the reverse of the process to put it back together. I'm not going to replace anything on here. There's 6 caps on here. I don't think they're bad. And I'm not going to go through taking the pots and the front faceplate and all that off just to check those couple of caps. I think they're fine. We're going to do some tests on the amplifier for performance, and if it passes the performance test, there's no need to mess with it. I did clean the switches and controls while I was in here, and that's it. So we're going to put it back together, and we'll be right back. Before I close up the bottom, I went ahead and replaced this bad capacitor, and if you remember, that across the line cap was this one here that, yeah, seen better days. So this is one of those self-healing capacitors, so if there is a problem with it, it'll never short out. And while I was in there, I also replaced the couple of electrolytics on there, even though I'm sure the old ones were still good, just like, because all the rest of them were good, I would have to think that these ones are good as well. But while I was in there, I did it. Going to button this up now, and we're going to go on to the other side. And the one last thing I want to check is I want to look at the protect relay and make sure the contacts on that are okay. They probably are, but I just want to make sure they're not pitted or if there's any problems like that. Alright, we have the right relay pulled out here, and it's not a real high-end relay. It doesn't have the gold contacts or anything like that. Let's take it apart. It doesn't look pitted, but it does look a little bit tarnished. These don't have the gold contacts on them, but it still should be okay. There you go. So there's our contacts. You can see they're a little bit dirty, and we should be able to clean them off a little bit. And even though this thing is supposed to short out to here, there are no contacts on this side here. So that's definitely not my favorite design. So maybe we'll replace this and put a better relay in there. Let me see what I have. Yeah, this is a much better relay. I think I'm going to put this in. It has the gold plated contacts on it. And there it is if you want to look at the part number. I don't know if you can see it or not. Hopefully you can. So that's it. We're going to put this in. Now there is one problem. This is a PC board mount right here, so you can see the pins are very narrow. These ones, the pin spacing is the same, but the pins, since they're designed to be plugged into a socket, are a little bit wider. So we will either have to trim these pins down or open the holes up a little bit on the board. And there's an awful lot of space on the board to do that. Let's see here. As you can see right in here. So I'm going to probably open those up a little bit with a little Dremel tool or something. Now I know I mentioned this in an earlier clip, but I'm going to go over this once again. Here is the protect relay, and this is what disconnects the amplifier from the speakers when there's an overload, so that you don't get any DC out to the speakers and destroy them. But if you notice, here's your contacts, those little thick black lines there. And when this pulls in, and it's pulled in right now in the schematic, it connects the output of the amplifier to the speaker terminals. But when it drops out, if you notice, the right and left set of normally closed contacts are tied together, and then they're tied to chassis ground. The reason for doing that is, once again, you want to take the speakers and ground them. So it's essentially shorting the speakers out. Why would you do that? Well, a couple reasons. Number one, by having this at ground potential, it is going to reduce the amount of arc flash when the relay contacts disengage under load. The other thing it's going to do is it is going to short out the voice coil of the speaker, which may have an inductive load on it, right? And it's going to also short out any of the reactive components in the crossover or whatever. So you're not going to have any kind of inductive or capacitive reactance taking place in the speakers when these contacts drop out. This is a good design. A lot of the protect circuits don't do that. They don't tie the speakers to ground like that. So this is a good thing to have. Where they went wrong was the relay that they used. These are dummy contacts for the normally closed. So even though they're touching these terminals, there's really no contacts in there. See the holes? Those holes are where the rivet for an actual set of contacts would go. So this was never intended to conduct current up here. So was not a good choice of a relay for this. The other thing is with those tinned plated contacts, those are very susceptible to tarnish. These gold plated ones on this new relay, much better, and they have an actual normally closed contact. And if I can move the camera to where you could see them, you can see both sets of contacts, the normally open and the normally closed. So what we're going to do right now is I'm going to rearrange the camera here, and we're going to turn this on, connect up the dummy load, and just make sure everything comes in okay. Okay, it's all plugged in. Let's see what happens. Power on. And there it goes. All right, good news. All right, let's try to put a signal through it now and see if everything's working. Okay, what they want us to do is to set the output, put a 100 hertz signal in there into the amp, turn the volume up and set everything until you have 9 volts RMS into an 8 ohm dummy load, at which point that should equal 10 watts. And then we're going to set those 2 pots that were sitting right next to that relay until you read 10 watts. So I can't get my head in there with the camera and do this, so I'm going to make the adjustment off camera. I'll put the camera back on there and I'll show you the results when it's done. Now I know we're a little bit of an angle here, but I have it set right on 10 watts on each one, but of course with the camera being at an angle it's hard to see. But that's it. I just adjusted these 2 pots down here with that signal, and you can see there's the signal on there, the 100 hertz, and that's all there is to it. Okay, like I said before, we're going to do one last test here, but remember I said we're not going to get into a lot of testing in this one. I'm just going to do a 1 kilohertz, and this amplifier is rated at 110 watts per channel. We're just going to close out the video making sure that it can hit that power rating. We're not even going to do distortion or anything right now. We're just going to make sure everything's working and we don't trip the protect or anything like that. So here we go. 1 kilohertz. Turning up the volume. And I have the 2 channels kind of on top of one another. And let's see if I can... And let me go. Let's see where we are. Well, there's 110.1 watts. And I think that's looking pretty good. 110.1. You go a little more, and there it starts to clip. So right below clipping, we're looking at 121.6. Not too bad. Okay, it's working. Both channels, and it looked pretty clean. I mean, obviously we have to do a distortion test. Clipping was pretty symmetrical. Of course, we just clipped it for a split second there, but I think we're good to go. So that closes out this epically long video. I bet you I have 3 or 4 hours of, I don't know, of footage here. I've been working on this for about a month, and in between I went on vacation and I've done all kinds of other things. So it'll be interesting to see how this thing turns out. But anyway, I wish you all peace, joy, happiness, and good health in your lives. We'll be back real soon. And in the next video, we're going to do some tests on this amplifier to see how it performs. Until then, take care. Bye-bye.